In this video, we'll be talking about centripetal force, but for vertical systems. So an example would be a rock. What color should I pick for a rock? Gray. A rock on a rope. And you're spinning this around some axis of rotation, or some place, or the center of your curve. Or you could also have a roller coaster. Let's draw this a little better. Or you could also have a roller coaster where you're driving your cart all the way up and around this roller coaster. So what's similar between your very, very familiar horizontal systems, like a car driving around a curve? Well, similarities is that your calculation for centripetal force is still equal to mass times velocity squared over r. So centripetal force still calculated the same. But what's different is that your normal force contributes, or tension force and your weight force can all contribute to your curve. So before, your weight force wouldn't contribute to horizontal systems. It would just be something that maybe would affect friction. But in these examples, your weight force can actually contribute to it, but at the same time, your weight force could also be the only thing that contributes to your centripetal force. And we're going to have problems on that for you guys. So let's draw a free body diagram to explain what I'm talking about. So at the top of your roller coaster, your centripetal force, or your net F net radial force, should point to the center. But a free body diagram like so this would be the top, would be a representation of what's actually going on at the top of your roller coaster ride. So you're going to have some normal force pointing down, but you're also going to have some weight force. And at the top, since both of these vectors point in the radial direction, or towards the center of the curve, your weight force and your normal force both contribute fully. So all the weight force contributes to your centripetal acceleration, or centripetal force. How about at the right side? So at the right over here, your free body diagram would look like so. So you're going to have a normal force that's perpendicular to the curve. You're also going to have some weight force. And in this case, the weight force, none of it has a component that is pointing in the left direction, or the radial direction. All of it's pointing perpendicular to the radial direction, so the weight force contributes nothing to the centripetal force. The normal force is the only thing contributing to your centripetal force. On the left, the very left of this curve, your free body diagram would look like so. It's going to have your dot in the middle, and it's going to have the normal force pointing to the right, and the weight force pointing straight down. And again, your weight force contributes nothing to the centripetal force. Your normal force is the only thing pointing in the radial direction, which is to the right in this case. But how about at the bottom, at the very bottom of your curve? Well, at the very bottom, your centripetal force, or your radial force, should point directly upward. What's actually nice about this is that your normal force points directly upward, due to the fact that it's always going to be perpendicular with the curve. But your weight force points in the opposite direction. And now you can see why I drew the normal force so small here and the normal force so large here. The reason why is because the weight force can actually take away your radial force. So it can actually, instead of contributing to the centripetal force, it actually takes away, it decontributes. I don't know the word. Uncontributes? It doesn't help. Okay. It kind of messes with the radial force, or the centripetal force. And if you were to subtract these two vectors from each other, this would be your net force here. And what's weird about this net force is that it's actually a lot smaller, due to the fact that the weight force is cancels out your normal force. So in this case, your normal force has to be a lot greater. So at the bottom of the curve, your normal force has to be a lot greater to counteract the weight force that is taking away from your centripetal acceleration. But at the top, since your weight force is actually fully contributing to the centripetal acceleration, the normal force barely needs to do any work. And in some cases, the normal force actually does absolutely no work. Your weight force is enough to contribute to your centripetal acceleration in some cases. And we're going to have some problems on that. But how about something? Maybe this is the elephant in the room for you and you've been scratching your head trying to figure out how to solve this. But what if you aren't in the top, bottom, left, or right? What if your weight forces and normal forces don't cancel out so prettily? What if you're right here, maybe 30 degrees from 30 degrees? This looks more like 45 degrees. Let's say you're 45 degrees counterclockwise from the very top. What if you're there? Well, the free body diagram will look a little weirder. It'll look like so, where the weight force is always pointing down, but the normal force will be pointing in the radial direction. It's going to look a little weirder, but the weight force still has some radial component that contributes to your normal force, but you don't know how to solve for it. Well, let's go ahead and solve some problems that will include these details. So I got this problem from OpenStax online textbook. If you want to take a look at the textbook and solve more problems, I'll leave a link in the description. But going on with this problem, we have a child with mass 40 kilos. So 40 kilos. We also have a radius of 7 meters. So this is the information that we're going to write down for this. At point A, the speed of the car is 10 meters per second. At the very top, the speed of the car is 10 meters per second. And at point B, the speed is 10.5. So the cart actually accelerated as you went downward. Assume the child is not holding on and does not wear a seatbelt. Okay, very stupid, very bad practice. Where are the parents? But that doesn't matter. They're not my kid. What is the force of your car seat on the child at point A? So at point A, we're at the very, very top of our roller coaster. And at the very top of the roller coaster, your weight force fully contributes to your centripetal force. And we're also going to have a normal force as well. And the normal force just comes from your velocity. So the greater your velocity, the greater your normal force. And that's because you're kind of, when you're traveling super fast, you're kind of actually going straight into the roller coaster a little bit, which pushes into the tracks, which creates a normal force. So this is what our free body diagram looks like. Let's find our weight force for the kid. So the weight force is just mass times gravity. So weight is equal to mg. And mass times gravity is equal to 392 newtons. So we have 392 newtons here. But in this case, the weight force is not enough to contribute fully to the centripetal force. The normal force needs to have some component. So let's see what the component of that normal force is. Let's see what the magnitude of this normal force is. So we're given information. Velocity is equal to 10 meters per second at point A. So we can actually calculate centripetal force by multiplying mass, so 40 kilos, by velocity squared over the radius. And then once you do that, let's pull my calculator out. Once you do that, you should get a centripetal or required centripetal force of 571.43 newtons. So once you have this, let's square it because it's actually important information. Okay, let's draw something better. This is very important to know because since this is a required centripetal force, our forces from the normal force and the weight force must equal the centripetal force. So the required normal force has to be, well, 571.43 minus 392. And then once you do that, 43 minus 392. Once you do that, you should get a normal force of 179.43 newtons. So 179.43 newtons for the normal force. And when you add the normal force and the weight force together, so when you add these together, you get the centripetal force. This actually makes sense in context. There you go, that's the word. In context of this problem, because these two are the only two forces in this free body diagram happening. So the components that are pointing in the radial direction must equal your centripetal force. And the thing about this is that your entire weight force actually points in the radial direction. It points to the center of the curve, and the normal force always points in the radial direction in these types of problems. So your normal force is equal to 179.43, which solves part A, the force of the car seat on the child at point A. Okay, we'll put the force of the car seat on the child at point B. Well, at point B, you're going to do things just a little differently. So let's erase everything we've done so far. So what are we going to do a little differently? Well, our free body diagram is going to look different. So our free body diagram is going to have the normal force point in the radial direction, and our weight force point in directly down, in the direction directly down. And the thing about this normal force is that it is, okay, let's draw this arrow a little more approximate. Thing about this normal force is that it has a 30-degree angle from the weight force. So this is 30 degrees. And the reason why is point B is 30 degrees from A. So if we were to draw the curve right here, let's try to draw the circle. If you were to draw the curve right here, your normal force is, oh, that's not actually approximate. Hold up. This looks a little better. Yes, the normal force is pointing to the center. Now, okay. So, looking at this is the curve right here. We form a 30-degree angle. Let's use green. Form a 30-degree angle with the point A, which is straight vertical. So if we were to draw a line from center to point A, it's straight vertical. And this point forms a 30-degree angle. Interior transverse angles claims that the angle between your weight force and the angle between your normal force and straight up, or the y-axis, should also be 30 degrees. And that's because both your weight force and the y-axis are parallel. So now that we determined that the weight force is 30 degrees from the normal force, what do we do? Well, there is going to be a component of your weight force that actually contributes to the centripetal direction. And that component looks like this. So you can separate this weight force to look like a triangle. And you can actually solve for this adjacent part of the triangle, adjacent to the 30-degree angle. This adjacent part of the triangle, which will contribute to your centripetal force. So F centripetal is equal to mass times velocity squared over radius. So your velocity at point B is 10.5 meters per second. So if you multiply everything together, you should get F centripetal is equal to 40 times 10.5 squared over your radius, 7. So 40 times 10.5 squared divided by 7 is equal to 630 newtons. So 630 newtons is your required centripetal force in this case. So in order to solve for the normal force here, so what is the force of the car and the seat? The car seat on the child, which is the normal force. In order to solve for the normal force here, we need to find your weight radial component. This radial component can be determined by weight is 392 times the cosine of 30. And the cosine of 30 will solve for the adjacent component of your, or the radial component of your weight force. And the radial component of the weight force is equal to 392 times the cosine of 30, which is equal to 339.48 newtons. Well, once you found this, you can solve for your normal force. And your normal force, again, is just the difference between the centripetal force and the component of the weight force that contributes to your centripetal force. So centripetal force subtracted by your radial component of the weight force. And that should equal, type in my calculator, 339.48. That should equal 290.52 newtons. So this right here is equal to the normal force. So that is the required normal force in order to keep your guy in a spiral. Now, if you don't have these normal forces, your kid will literally just fall off. So let's not have that happen. Let's drive fast enough on the roller coaster. Okay, let's solve for part C. What is the minimum speed required to keep the child on a seat at point A? So at the very top. Well, what does it mean by the minimum speed? Well, the minimum speed required to keep the child seated at point A would mean that the weight force is the only thing contributing to the centripetal force. So let's say you're in a spiral, right? You're going around this roller coaster, and at the very top, you technically become weightless for a moment. You technically become weightless. And the reason why is because, well, you're in a kind of instantaneous state of free fall, where there is no normal force. There's absolutely no normal force going on. The weight force is the only thing contributing to your centripetal force. So let's solve for that. That just means that mg is equal to mv squared over r. Right? Your weight force is equal to your centripetal force. So we can actually cancel out our masses, and we'll get left with g is equal to v squared over r. If you want to isolate velocity, you just get the square root of gravity times radius is equal to your velocity. So the radius is equal to 7 meters. So if we find the square root of 9.8 times 7, you will get a velocity of 8.28 meters per second. So this is the minimum. This is the minimum velocity required to keep your child in his seat at point A. So in this problem, you have a modern roller coaster. So radius is getting a little smaller at the top, and the radius is at its maximum at the bottom. So it kind of gets thinner as you go up the roller coaster, just due to some practicality reasons. And also safety reasons. But let's ignore the front of this problem. It's completely useless. We just need to know what is the speed of the roller coaster at the top of the loop if the radius of curvature is 15 meters. So let's write that down. And the downward acceleration of the cart is 1.5 grams. Not grams, 1.5. Oh, I've been doing too much chemistry. 1.5 G's. So what's actually happening at the top of the loop is that your only centripetal acceleration going on is straight downward. So the downward acceleration is equal to 1.5 times our gravitational constant. So let's write down centripetal acceleration formula. So we have a centripetal times v squared over r. And we need to find the speed of the roller coaster if this is the acceleration. So the acceleration is in this case, is equal to 1.5, not 15, 1.5 times 9.8. So 1.5 times 9.8 is equal to 14.7 meters per second squared for acceleration. And now that we have the acceleration, well, we can solve for everything. We have 14.7 is equal to v squared over r. R is our radius, which is equal to 15. So if we multiply 15 by both sides and we square root it, we'll get 14.7 times 15 is equal to our velocity. Technically our, not minimum velocity, our velocity given this centripetal acceleration. So now that we have all this, just plug into your calculator and your answer is there. Okay. Velocity is equal to 14.85 meters per second. And this is all due to your downward acceleration given. So, as always, if you have any questions, put it down in the comment section. I hope this video helped.